Okay, so before it starts, do you see this balloon videos? Scale balloon. These are some of your fellow students. I don't know if you recognize some EECS students there. Let's move on. Lots of sitting, filling balloon, and then releasing it. Okay, I'll move it. It's kind of nice, huh? And okay, moving on. Let's just move to a part where we reach space. What do you think about that, huh? That's about 100,000 feet. That's how much it reached. So the skies are black. Right? Unbelievable. So I was tracking, and it's the Sierras, I think, like far away. It only reached the middle of the Central Valley, actually. I think it's just beautiful. And all the time it was sending these APRS packets tracking the position, I was able from home, actually. My home station was, receiving all these packets. So I thought was pretty cool because I was uploading them to the web. So it's like says my, you see actually that I was really proud of my station. So I think is a really nice thing that you could do. You were going to implement APRS, a modem that could do this protocol to send these packets that reports these positions, be able to decode them too. So you'll be able to do that, without an extra software. You actually will build the physical layer of this type of a protocol. Anyway, just to give you a heads up of what you could be doing if you really wanted to. And switch. No. Okay, so welcome to EE123 lecture. Is that the right class, right? Yeah. EE123 lecture 22nd. Woo! Okay. So the stuff we're going to talk about today is the Lab 4, and also I decided that. So usually I talk about compressed sensing at the end of the class. I talk about 2D at the end. I figure actually in the middle is a better time, because by the end you're kind of like it's like let's just get over with. We want to study for the midterm and so on and so forth, or you don't get things in context. And since we covered sampling, we covered wavelet, we covered 2D, I think it's a really appropriate time to talk about compressive sampling, which is kind of a next generation of sampling theory. And I will. We're not going to, again, go into huge depth, but I really want you to know about this. So then you can take more advanced classes about this topic. So we're going to spend some time today and also on Friday on this topic. Then we're going to move to filter design after the spring break. Okay, so I think it's a really nice thing in the middle that we could spend time on. Again, just a balloon. This is a balloon launched by Berkeley students. It was launched from campus. It flew over Tilden Park along this, actually around Highway 4 that goes east. Just really along Highway 4. It reached this part of the Central Valley just after Stockton. I think Stockton is around here. And then it just slowed down and slowly starting to climb up and up and up and up because of the hills, the way the air is. It's just didn't move, and just going like up to 100,000 feet. Then it was I think they have some way to release either by height or by other means, and then it released the helium, and then it started going down and landed somewhere here near the town of Coppertown, something like this. And it was retrieved only the next day because they couldn't find it the first day. So while it was moving, it was sending packets, APRS packets, which this particular website tracks. This cool website also gives you prediction based on atmospheric, and it was really following those predictions. I was just amazed how they know this thing is going to land like hours before. And like it predicted all this, going around here and everything. It was just, really almost on. I thought it was pretty cool. Yeah.
So the website did all the mapping for it. You were picking up. You just
yes.
All of
I was just picking the signal and then uploading it to the web to aprs.fi, and then that's been aggregated and input and predicted and all sorts of things like this, which is really, really nice. So yeah, APRS is actually, so this is a nice, there's this people that put these stations. So you as a person that wants to track something, you can leverage this. You can leverage the infrastructure that amateurs has put out, kind of crowdsourcing in that sense. Yep. That's the like a space something student group here on campus. They have a call sign. One of their student, the student in that group, I think it's his call sign that they were using for this experiment. But you can join these experiments and you can be part of it. You can have your own. I think it's pretty cool to actually put like cameras in space. You can also put a repeater, for example, if you want to put that. And then there's lots of things that you could do. Send pictures like SSTV, one of the projects. Options will be transmitting images over a wireless communication channel. You'll be able to do something like this afterwards too. So anyway, just food for thought. Also, we're being blasted by the sun. There was a Sunday, there was a solar flare, a solar storm. Now it reached Earth. If you look at the bands, quite poor. So there's a lot of disturbances in the force. Do you sense it? I sense this disturbance in the force. Right? Yeah. Obi-Wan should have taught you well. All right. So Lab 4. Let's talk about Lab 4. So one of the problem is that the SDR crystal oscillator really often has a certain offset. It has an offset because it's not a really great crystal. It's not very accurate, but also unstable over time. So just because of heating, it will kind of drift over time. Cell phones crystals also do the same thing. They're not that expensive. They're very hard to actually create something that's very stable on a mobile device. Okay, so they're not stable. So what happens is that you think you are at demodulating or listening to a particular frequency, but you're a little bit off. Okay, but all the software thinks that it's doing this. So the GSM protocol, which is a protocol for like a 2.5G protocol for a cellular communication, used mostly, it was developed in Europe. Europe really uses it, but also AT&T, Singular in the past, now AT&T uses the GSM network. I think also T-Mobile, GSM phones. Has a built-in synchronization such that the phone can synchronize itself to the frequency of the base station. Base station can have a very accurate clock because something that's stationary, has lots of power, that's not a big deal. Okay, you can actually put, and there's not that many of them, and cost is not as an issue as a phone, where a lot of people want to buy, and that's consumer product, right? So you don't want to put something expensive on the phone. So a base station will have very accurate synchronization signal, and you want to be able to sync to the base station. The first thing the phone would do is that. Okay. GSM 850. That's the one that's the format that's used in the U.S. and it's why 850 because 850 megahertz. That's the frequency that's operating at. So this frequency band has frequencies. It's split into channels. Each channel is 200 kilohertz, very much similar to FM radio, but here for GSM. It splits the frequencies into uplink frequencies. So that's the phone will transmit to the base station. And a downlink frequencies where the base station will transmit down to the phones. Okay? Why is it 50 megahertz away? It is about, 45 megahertz away. Hello, EE123. And then you have to answer. And then, how are you? If we use the same channel, we can't really make a conversation that is duplex, right? We'd like to transmit and receive at the same time. Okay? So if you want to transmit and receive at the same time on a single device with a single antenna, it's very difficult to do that on the same frequency. It's very difficult. Excruciatingly difficult. People are trying to, but it's super difficult. So what you like to do is to have some filtering between the receiver and the transmitter. So if you're transmitting 1 watt, through the antenna, and you're picking up, microwatts at the same time, you want to make sure that you can isolate those signals very well. And as you know, if you implement an analog filter, it's going to have some transition width, and it's going to, depending on how do you create it, it's really good if the frequencies are far away from each other. If they're 50 megahertz away, you have a chance to do that on a phone and get really good isolation. Okay, so this is one of the reasons. Okay, so the way the way this protocol works is a time division multiple access. So on the same channel, you can have 8 conversations that are happening apparently at the same time, but they're interleaved in time. Okay, but they're interleaved in a rate that we don't, as humans, don't recognize. So it's faster than what we can observe. So that's not a problem. So what you have is you have these what's called a TDMA frame, time division multiple access frames. Each one is called is its name, and this is all in the document that you're going to get. Okay, so it all explains there in more details. But I just wanted to give you kind of a heads up because you're going to have the spring break, and maybe you want to work in the lab because it's so exciting. What was the point? I want you actually to understand what it is, not just from that. Anyway, so each one of these frames is 4.615 millisecond long. A total of 8 frames is 569 microsecond long. Is that right? No, sorry. Each one of these frames is 579 microsecond, and the whole frame, the whole 8 frame together is 4.6 millisecond. Okay, so you have time slot 0, time slot 1, and each phone is allocated a time slot. Yeah. Pardon? That's the uplink, and that's the downlink frequencies. Yeah, it doesn't make sense, right? I think, yeah, it makes sense. It doesn't matter. It's a range. Still valid. It just goes down. Downlink. I don't think it goes to 893. I think actually it's 49 to this. But maybe you're right. I need to check. And if I check and you're correct, then you know what you get. Okay. So then, where was I? Yes. So each one of these frames, basically each phone will transmit on a frame. Okay, so you can have a few phones transmitting on the same channel. So that's how you share a channel. Okay. Now each one of these will have what's called bursts. Okay, the phone will burst in and it'll send some information. A normal data burst will consist of a guard time, so time that there's nothing there. The reason that there's nothing there is because you're driving with your cell phone. There's some delays. There's some delays in the clock of the cell phone itself. So all of these might need to be compensated so that there's no overlap between frames, and so phones don't overlap on top of each other. So they leave some guard time, so it starts immediately. So this is kind of to save things. Then you've got 3 bits. So time corresponding to 3 bits, that's also 0. They're not supposed to be anything. Then you've got here data, 57 bits of data. Then another empty bit. Then a training bits. So 26 known bits, okay, that you know what they are. And then 1 bit, and then data, and then another 3 0 bits, and then guard time. The training bits are used for the receiver to estimate what the channel is. So channel has distortions. You know what the data should be in this time, so you can train a filter to compensate for all sorts of distortion, atmospheric distortion, delays, and multipath, and all sorts of things like this. Okay, equalization. If you have attenuation at different frequencies, you can actually fix that. Okay. Yes.
The 257 bits of data, is it the same data?
No. This is used to transmit data. It's just on both sides of the training. Yeah. So you don't put the training on one side; you put the training in the middle between them. So, so the thing is, these disturbances are non-stationary. They change over time. So you really want to be able to capture them over and over again. That's why they spend quite a bit of bits just to do this training, so it's robust. Okay, think about that. Then you also have other types of bursts. One of them is called a frequency correction burst, and this is what we're going to be looking at. What it does, it has, again, guard time, 3 bits, and then just a constant frequency for 142 bits. The way bits are encoded is what's called a Gaussian minimum shift keying. But the point is that if you transmit a bit, I think it's 0 over and over and over again, it's basically just a constant frequency. Okay? That's what it comes down to be. Okay? So this is basically constant frequency for almost 576 79 microseconds. Okay? So about half a millisecond of time, you've got this pure frequency. And this is meant basically for calibration. Okay, so to calibrate the frequency, because this is a known frequency, and so when somebody receives, it knows what to expect. And if you have an offset, then that means that you know how to correct them, and that's what we're going to do in the lab. Okay, so where do these appear? There's what's called a control channel multiframe. So if you think of packets being sent, these chips of time, right? This is what's called a multiframe. There's 50 multiframes, and this is a single frame. So within this will be the first time allocation, then the second time. All of these are about 4.6 milliseconds. 4.6 millisecond. This is transmit, and then this one transmit, this one, so on and so forth. Okay, these are transmitted over time. Okay, these are the time slots, and once you finish this frame, then you've got a multi-frame of 50 that's split into 50 pieces, and then it repeats over and over again. So what you've got, this is the control channel multi-frame, and so the frequency correction bursts are transmitted by the base station at time slot 0, at frame 0, 10, 20, 30, 50. Okay? And then, 40, and then once it finished 50, then it's going to start, again. Okay? So this is 4 milliseconds, 4 milliseconds, 4 milliseconds, 4, and then, after that many milliseconds, you've got a burst. And then 4, 4, 4, 4, 4, 4, 4, and then you've got a burst, and so on and so forth. Okay? Now, these bursts are pure frequency at 67.7083 kilohertz offset from the center frequency of the channel. Okay? So remember, the entire spectrum allocated for GSM is split into 200 kilohertz channels. If you tune to a particular channel, and you tune to an offset of 67.7 kilohertz, you should be hearing this tone once in a while. Okay? It's always at that offset. That means that if I tune to a channel and I hear something like a pure tone not at that offset, I will be able to correct and find the offset. Then I can correct my own oscillator, okay? My own frequency based on these measurements. So here's an example. This is using one of the SDR software, using this. Okay. This is how a GSM base station looks like. It's kind of like, you see that it's kind of look like a lump that is about 150, almost 200 kilohertz wide. Okay, because each channel is how much, that's how much each channel is. Okay. You will see within the GSM, like the cell phone frequencies, you'll also see these things like are wide. These are spread spectrum, like 3G, 4G, LTE, all this stuff. This looks like that. So this is not GSM. Okay, but you'll also see within this bandwidth, you see this. This is actually how GSM looks like. And you'll need to look for them in the lab. You need to look for a channel that looks like that. You're not going to do that automatically. So now, if I, let's say I tune my receiver to the center frequency, which is 869 point, I think 2. Right? It's every 200 kilohertz. So 869.2. Let's say I tune. Then here's what you see. This is the spectrum that I get. And you see that the spectrum is not centered. This is not exactly the same one as this one, but this one I used in NumPy in IPython notebook. So I tuned to the center, and I expected the shape to be in the center, but obviously it's not. That means that my oscillator is off. Okay, it is not centered. So somewhere something is going on. It should have been centered. Okay? So what I want to do is I want to find what is my offset. Okay? If I find my offset, I'm good. Now this is the magnitude of the time signal. Okay? Look at this. You'll have to plot the magnitude of the time signal for slightly longer than the time that it takes for 8 frames to appear. Okay? And how many frames do you see? Do you see the frames? See the guard time? The guard time when nothing is transmitted? Here's guard time, guard time, guard time, guard time, guard time. Nothing is transmitted during this time. You actually can see it in the magnitude. And then you see a packet, like a slot. Okay, that's pretty cool. And you count 1, 2, 3, 4, 5, 6, 7, 8, yay, and a little bit more. So yeah, this is actually what I predicted. So you're going to be plotting this too. And you're going to see this. Now, the classical thing to look for a frequency that appears over time, what is it? Like, what would we need some time frequency analysis. What do we do? Come on. Short time for a transform or a spectrogram, right? Yeah. So what you're going to do is you're going to create a spectrogram, and you're going to look at the spectrogram. And do you see those frequency correction bursts? So there's a lot of crap going on, but at some point, you see? Blip, 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 blip. Okay? These are frequency correction bursts. They're pure frequency because there's nothing. You see, it's black except here. That means that it's a pure frequency at that time point. Cool, huh? So you can actually see the frequency correction bursts. And then the idea is that you can tune to what this frequency and then correct for it, right? Now the thing is, computing a spectrogram is pretty expensive. Lots of DFTs over and over again, over and over and over and over again, right? So it's computationally intensive. So we're going to take a slightly different approach as doing this. What you're going to do is, after you look at this, you're going to figure out, okay, I have some sort of an offset. This was supposed to be at 67 kilohertz. It was supposed to be up here. This is 50 kilohertz. It was supposed to be at 67 kilohertz. However, it's more like at 30 kilohertz. So I'm 30 kilohertz off. Okay? right? This is 50 kilohertz. It's supposed to be somewhere here. But now I'm actually measuring here. So I'm 30 kilohertz off. Okay? So you're going to look at this and you're going to remember that. I'm 30 kilohertz about off. Okay? What you're going to use instead, we're going to use basically bandpass filtering, and in order to figure out where those frequency tones appear. We're going to create a bandpass filter that is around this frequency. Okay? And so whenever there's going to be a frequency correction burst, we're going to see signal coming out of that filter. Otherwise, we're not going to see anything, or just maybe noise, slightly. Okay? So we're going to create a filter. Now, filtering is much faster than computing DFTs over and over again, right? But it doesn't give us the accuracy. Okay? So we're going to do filtering. We're going to use the filtering to detect where those bursts occur. Once they occur, we can get those samples, and then using DFT, compute what the actual frequency offset is accurately. Okay? So we're just going to compute the DFT on the time where these frequency bursts occur. Okay? Any questions? So we're going to design this bandpass filter, and after you pass through the bandpass filter, and you're going to look at the magnitude after bandpass filtering, you're going to see whenever you have a frequency correction burst, you've got a, boop, boop, boop. And actually, you hear it, you listen to it. If you put a narrowband filter, you hear like ta 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 ta. I'll actually do a demo for you now. You'll hear like a ta 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 at the rate that it's playing. So you see this. And this would be the spectrum of this thing. This is after filtering, right? So I filtered around 30 kilohertz. You see, this is 50, this is 30 kilohertz. This is what I filtered by. Okay? All right. Now, the thing is, you want to look at those, the location of these, right? So there's computation that you need to kind of figure out where they are, and the rate is pretty high. But what's the bandwidth? This is the bandwidth. We've got sample at this rate. Doesn't make sense, right? We can represent them using a lower rate. We can actually downsample them and not get aliasing, because this is the bandwidth. Okay? So what we're going to do is we're going to decimate to do the processing at a lower rate. Okay? So after decimation, you're going to go from here into the filter decimated signal spectrum, right? So now your spectrum aliased after decimation to zero frequency, right? It keeps on replicating, right? Based on how much you decimated. So what's going to happen is that you need to figure out where that center is aliasing to, based on how much you downsampled. So you need to figure out where it's aliasing to. So this is now we have the signal at the lower rate. Once we have it at a lower rate, this is how it looks like. Okay? Then you can threshold, and then whatever is above a certain threshold, you're going to take those samples, and you're going to compute the frequency using a zero-padded DFT. Zero-padded DFT is to get a really better accuracy of the DTFT. So you get better accuracy of the frequency estimation. Okay? So you detect those. You compute the frequency, and this is the frequency in the aliased, not alias, but at the downsampled version. You need to figure out, though, to what frequency, original frequency, this is mapped to. So you need to do some calculations. Okay? Once you do that, then you've got your frequency. You got it right. You might probably going to average over a few bursts, because you have a lot of bursts. So you should, just not compute one. You will average a few of them, and you'll get your frequency. Okay. So this is the whole process here that you're going to go. Okay. Yes.
So why do we want to downsample it and then do the calculation? Can we just do it without downsampling?
We could. But what are we trying to save here? What's the rate that the samples are coming in? 200 kilohertz at least, 240. You're going to sample at 240 kilohertz. Right? But you're going to filter to like 32, like your bandwidth is actually occupying 1/32 of the entire bandwidth. Do you really want to operate at 240 kilohertz, like compute so many samples and do all the thresholds? And you want to do that in real time, right? A phone needs to do this. If you have 240 kilo samples per second, I mean, this is too much for a phone. It's going to heat up. Steve's going to be upset. You're going to be upset. The battery runs, so, it's not good for anybody, right? You really don't need that many samples, right? So you're going to downsample, right? We filtered, we can downsample. That's the whole point about, filtering, right? Once you have a narrow bandwidth, you can then process it on the smaller, on the lower rate. So that's what we're going to do. Okay, so it brings together, though, all the stuff that you kind of covered. Now, I'm not going to ask you to implement a polyphase filter, which is actually pretty easy, but it's probably not going to give you much benefit in the Python environment. Okay, if you implement things in C, C++, that will be faster. But in Python, there's all this, there's the interpretation stage and so on and so forth that you don't know exactly what's going on. So it might not be that faster. So we're not going to do this. But the real problem is that, what if now you don't know what the offset is, right? We did this narrowband filter. There's going to be a trade-off. I can use a bigger filter, a wider filter, but then, I get more noise. So the peak is not going to be as high compared to the rest of the crop. If I have the filter narrow, then, I might miss the peak where it actually is. So what you're going to do, what we call a mini project, is you're going to do a filter bank. Okay? You're going to assume that there's going to be maximum of 50 kilohertz offset, and you're going to create filter bank of narrowband filters around this, and you're going to run through all these narrowband filters, do the detection in the decimated version. Right? So the cool thing about this is that the amount of computation you're going to do is much lower because you're operating at the lower rate. So again, you're going to implement a filter bank to do this. But once you created, one filter, then doing a filter bank is quite easy because you just replicate, the code for the rest. Okay. So that should be relatively nice. Let me just show you an example. GQRX, and this is how it looks like. Any questions? It's really cool, I have to say. It's a really cool project, lab. We definitely guide you through it, so I think it should be relatively straightforward, but sometimes it's not as straightforward. So let's first look for a GSM base station. I want to make sure that the gain is right. Oh, there it is. See? This is actually a GSM base station because this hump. See this hump? That's another one. Actually, this one and this one is another one. Okay. Why can't I hear anything? They could overlap, yeah. They could overlap a little bit. They don't overlap completely, but they overlap a little bit. I'm not sure why I can't hear anything, because I wanted to show you the clicks and stuff. Output, headphones. And the audio here is fine. It's this. And are we setting here something? Huh. That is strange. These demos are really not working for me today. Let's try again. So I think this is good. Oh, I think I know why it's wrong. I think my output, no, it's, okay. one last time. Any questions so far? This is GQRX. It's a software-defined software-defined radio program, which I don't know why it doesn't actually makes the sound. I can't see it for some reason. I don't think it is. Yeah, Squash is on. You ready? So what I'm going to do now is I'm going to zoom in. The frequency here is supposed to be 874.4, but it's a little bit off. So what we're going to do now is we're going to zoom in a little bit, and I'm going to also make sure that the FFT has enough accuracy. It does. Okay. So now I'm going to tune into here. You hear it? You hear the clicks? Yeah. So the clicks are at 0.65 instead of 0.67. Actually, no, sorry. This is 6 is good. It's supposed to be, so this 6 is good. It's supposed to be at 67 here, but it's 58. Okay? It's supposed to be at 67, but it's 58. So that means that it's about 10 kilohertz off. Okay? So this thing has, I can actually correct for ppm. You know, if I correct for ppm, that's going to change. Mostly going to change. I don't know. Anyway, so there's the ability to, within the driver, to correct for these kind of shifts. And so you can actually call, and with the, after you figure out what the value was, then you can change. So you hear it? It doesn't appear here. It doesn't appear here. Those clicks appear here. Okay? So that's the point, is to tune and figure out what is basically the frequency offset. So I think this is a lot of fun and pretty rewarding. It was inspired actually by a piece of software that does a similar thing, although they use a more adaptive filter to be able to figure out what the frequency is. But this filter bank is quite an efficient approach to it. Okay? So I hope you enjoy this one. At least you learn a little bit about, how cell phone networks actually operates, which I think is definitely useful. And you're going to do the first thing the phone does when it tries to connect to the network. First thing it does, it looks at the frequency. Then it does some time, and then it starts negotiating, time slots, and then it starts transmitting. Okay. All right, we don't have a lot of time, so I'm going to start talking about a topic which is really deep to my heart because I've been spending on this topic about 10 years, if not more, of my career. Part of the reason actually I'm here is that I was working on this topic, so definitely a hot topic in the area of signal processing in the last 10 years. So the topic is called compressed sensing and compressive sampling. And so far we've talked about sampling band-limited signals. Right? We have a band-limited signal. There's the Nyquist theorem that says if the signal is band-limited, if you sample twice the highest frequency, you'll be able to represent the samples, right? So the question really, if I have a signal, a time signal, and it could be anything, and it's band-limited, what is the rate that you need to sample it at? At least. What's the highest frequency, right? At least the Nyquist rate. At least. You can sample faster if you wanted to. And we saw that there are reasons why you'd want to sample faster. Right? If you oversample, you get something out of it. But that's for anything. Let's say somebody's transmitting a band-limited noise. And you want to sample that band-limited noise. You'll be able to accurately represent this band-limited noise with those samples. Okay? So that's sending anything, really. Doesn't matter what you send, you'll be able to recover this. And so then the question is, like, if I not send anything, I said just something. Right? Not anything, but something. And that something cannot be anything. That's the idea. Right? Then, what is the rate that you need to sample at in order to faithfully reconstruct the signal from these measurements? What? Well, it depends. Yeah, it definitely depends, right? That's my favorite answer, by the way. When you ask me, especially if you ask me something about MRI, I would say, it depends. But I would say, maybe if you send something, I can sample below the Nyquist rate and still be able to reconstruct. Okay? Here's an example. What if I send you a narrower bandwidth signal? Okay? Then really the Nyquist rate is lower. What if I send you a band-limited signal that it's not a low frequency, but it has a bandpass, right? It's just between particular bands. Maybe. What if that signal is, made out of just frequencies that have a certain spacing, so that if I sample, they don't alias on top of each other, right? Maybe. So maybe I could do something, but I need to know kind of where things are, right? So here's kind of a question that comes in. Okay, here's the motivation. Let's say you're given samples of a harmonic function. And you know that there's only one frequency. Okay? Just one. The question is this Nyquist sampled? What do you think? Yes or no? Is this Nyquist sampled or not? Raise your hand if you think that it is Nyquist sampled. Raise your hand if you don't think it's Nyquist sampled. Raise your hand if you just don't know. Well, you can guess, though. Well, let's see. The Nyquist sample is twice the highest frequency, right? That means that in a cycle, how many measurements I should have? 4. Right? So 1, 2, 3, 4. Yep, in a cycle. Actually, at least you're right. Just over 3. So you need to be able to basically, this is a cycle, full cycle. You'll need to see, have a sample just before when it changes. Before it goes down. Okay? So actually, you're absolutely correct. You need just over 2. Okay? So this is definitely over 2. This is 3. So this is Nyquist sample. So how can I reconstruct this? How can I reconstruct the continuous signal? Yeah, with convolution with a sink, right? Convolution with a sink. Great. Okay. So now, instead of collecting samples at that rate, I'm going to collect half the samples at half the rate. Okay? So total of half the samples because I'm going to sample at half the rate. And the question is this Nyquist sampled? So I sample here. The red ones are the sampled ones. Okay? So I missed this one. I didn't collect that one. I only have samples of this one, this one, this one, this one, this one, and so on and so forth. Is this Nyquist sampled? Who thinks it is not Nyquist sampled? Who thinks it is? Who's confused? Who just doesn't know? Let me argue, yeah, you're absolutely correct. Those who said that it is not, because I really don't see when it's going down. It could have gone down here, right? But what it did, it went down and then up, but I just missed it. Okay? So I could fit a sinusoid that looks like this, that is lower frequency, but still fits those values. So I went to a lower sampling rate, and let's say I'm telling you, hey, the frequency cannot be faster than, much faster than this frequency, right, the original one. Okay? Then basically the original Nyquist rate. The frequency cannot be faster. And I'm telling you, there's just one frequency. Just one. Can you recover from measurements? Can you recover the original one from the measurement? There's one frequency. You know that there's one. But what's the problem?
So you're saying we're choosing either low or react?
You don't know. Right? Within this bandwidth, there's two options. Right? Within the bandwidth, you know there's one frequency. But there's two options. They're equally likely to be a right option. So you have 50% chances of being right or wrong. Okay, there's inherent ambiguity there. That's what's called aliasing. The high frequency aliases to the low frequency. Right? Alias to low, it appears as low frequency. And even though I'm telling you it could be higher than this, but you just don't know. Was that the low one? Was that the high one? I have no idea. They are going to look exactly the same when I sample at this rate. Right? So I made half the measurements. And now I have double the ambiguity. But what I really want to is, well, if there's just one frequency, what can I do to make half the measurement still? Okay, half the rate. And still be able to recover. What do I need to remove? That's the problem here, right? The problem is the ambiguity. I want to remove it. So if I know that there's just one frequency, how can I remove the ambiguity? Yeah.
You sample at different intervals.
Ooh, I like it. Nice. So if you sample at different intervals, still half the rate, but different intervals, what would happen? What do you want to do? Let's move one sample. Okay. Let's move this one to here or something, or maybe Is that what I drew? Yeah. Yeah. Let's move this one and actually measure this point. Okay. Not measure this point. Measure this point. Okay. All right. Now I sampled at half the rate. I have less. Well, it's not really half the rate, but I have half the number of samples. But what did I resolve? I resolved the ambiguity between these two, right? Now I can say, it's definitely the highest one. Cannot be the low one. Solved it. If I have one frequency. What if I have more frequencies? Can it still go through these points and not be? Can I have a signal that goes through these points and not be this one? Yeah, right? They could be. How can I resolve that? Maybe I can maybe move another sample, right, or something, right? But then it becomes more tricky. Okay, how can I make sure that I don't overlap with some possible signal that could be likely as well, right? But you can definitely see that if you have a certain model, the signal is something, then you could do something about that and go for a lower rate. Okay? So in the last 30 seconds, I'm just going to give you a motivation of why is that? What's the whole idea here? The whole idea is that things, most signals are actually something. Okay? Most things are something, and because there's something, we can exploit that. For example, if you take a picture with a digital camera, you acquire all the pixels, okay, on the CCD. You get this beautiful girl's picture. I can't believe they've changed so much since I first gave this presentation. They're now 7-year-olds. Actually look like human beings. Wow. All right. So then, I'm shocked how much I'm older than. All right. Then you take this and you compress this. Your digital camera does it all the time. Represent it using smaller size. How can you do this? This is, if you think about downsampling, it's not like it's a lot of calculation to downsample, but if you think about conceptually, what am I doing? I'm changing the rate of my measurements. I started with a higher rate. I go for a lower rate. It's not uniform. It's not, it's not like, filtering. There's a lot of processing is going on there. But you're starting from a higher rate, and you're going to go to a lower rate. And you're not losing information. Okay? So think about that. If you think about that, and in the context of my area, it is also true for medical imaging. And in medical imaging, this is really expensive. To acquire all the data and be able to reconstruct. That's expensive. But if I know that I can then take this and go for a lower rate, the question is, can I go to a lower rate from here to here? Just sample it in a lower rate. And then once I know, because I know it's compressible, then go from here to here. Okay, this idea is called compressed sensing. It's due to Dono and Candes. There's a lot of research before that, but they were the first actually to prove some mathematical theorems about this ability to do so. And this is what we're going to talk about next time. By the way, it doesn't have to be images. Right? Could be videos, where you have to sample both time and space. Okay? So next time, on Friday, we're going to continue talking about this. We're going to talk about the concepts of these ideas. I'll show you what's the idea to how to reconstruct and what's the mechanism of doing this. All right, see you on... there's an excellent talk right now for the EECS colloquium that I do recommend going. It's in HP Auditorium. A colleague of mine that is doing work in the MR, mostly on neuroscience, and I really recommend going for those who are interested. It's happening in about 8 minutes. It's going to start. And sorry about this. Just ignore what I just said and go to Frank's session. Sorry about that. It's going to be recorded online, so you can watch the... Sorry, Frank.